Welcome to the deep dive. So today we're jumping into something called the hydroplane paradox. It's all about why ice is slippery. And, well, it pretty much turns what you learned in high school physics completely on its head.
That's exactly it. You know, that whole idea that your skate's pressure melts the ice, the squitch to slip theory.
Yeah, that's what we're all told. That's what I thought.
Turns out that's not really the full picture. The new research points to something much deeper. It's foundational. It's quantum.
Right. So our mission for this deep dive is to unpack this new model. It talks a lot about information exchange and something called pre-contact physics.
Let's get into it.
So what's the core discovery here?
Okay, so here's the aha moment from the research. The slipperiness, the slick layer, it actually happens before your skate physically makes contact.
Wait, how is that even possible? If there's no squish, no pressure, what's creating the slip?
This is where the Fox quantum geometry model comes into play. It suggests that as any object gets close to the ice, something at the surface they call the Fox coherence density, or FCD, it drops instantly.
FCD. Okay, let's translate that. Is that just a fancy way of saying how tightly packed the water molecules are right at the very top?
Essentially, yes, but it's better to think of it more like a regulated energy field. As the skate blade enters that field, the ice reacts defensively.
Defensively.
Yes. That coherence density plummets, and that creates a tiny, perfectly lubricated gap. They call it the matter of change layer.
So it's like the ice and the skate are having a conversation before they even touch.
That's a perfect way to put it. It is an information exchange. They register each other and react before contact is ever made.
And the ice is actively creating this buffer, this hydroplane interface. Why? To protect itself.
Exactly. It's what's called an emergent property. The ultimate goal is to maintain the stability of its internal crystal structure.
It sees the skate as a threat.
As a disruptive force, yes. So this interface acts as a shield, a coherence density buffer that absorbs the potential strain.
And this is where the really big math comes in. The papers reference FCD being approximately equal to mc squared. I mean, that's Einstein. What does relativity have to do with an ice rink?
Well, this is the quantum implication that's so fascinating. In this model, information has mass.
Information has mass.
Okay, so when that FCD shifts, when the ice is exchanging information with the skate, it's a literal redistribution of mass and energy on a nanoscale.
Wow.
They actually call it the hoverboard effect because that density drop generates a tiny repulsive lubricating force.
And that's the final nail in the coffin for the old pressure melt theory.
Precisely, because we know ice is still incredibly slick at, say, minus 100 degrees Celsius.
Where melting is physically impossible.
Absolutely impossible. This quantum layer, this information exchange, is the only explanation that holds up.
Okay, so let's just boil this all down. The simple takeaway. Ice isn't slippery because we melt it. Ice is slippery because it's a smart, self-lubricating system.
It pre-greases itself using quantum information.
Right. It's not an accident. It's not a flaw.
No, the hydroplane is the protocol. It's the ice's built-in directive to maintain its own integrity.
Which leaves us with a final thought for you to take away. If something we think of as so simple, so fundamental like slipperiness, is actually this incredibly sophisticated self-governing protocol.
A protocol driven by information density and mass energy equivalence.
Then just consider, how many other everyday physical phenomena are actually the result of complex, protective quantum protocols happening right under our noses?